So here's something that we talked about last time in 5.2. We said, don't look at that. We said, if we have some polynomial function, we can talk about X-intercepts, right? X-intercepts are just where it intercepts the x-axis. All right, and we set the function equal to 0. Right? X-intercept is when y is 0. Y-intercept is when x is 0. Okay, we also talked about Y-intercepts. We found those, no problem. We also talked about something new called turning points. And turning points are these parts in the polynomial, the humps, the hills, the valleys, right? It's where it goes from going down to starting up, or from going up to going down. All of you, I'm sure, are familiar with your own turning points in your own classes, where you may have not been doing all right, but then you hit a turning point and you started soaring to the moon. Okay, and that's what turning points are. So we're going to talk a little bit more about turning points today. So there's a little property, a good little property we got here. And this property says that a polynomial of degree n, wait a minute, degree n. What the heck is the degree of a polynomial? Remember, the degree of a polynomial is just the biggest exponent of the x's, okay? So remember, we talked, not yesterday, Friday, right? This polynomial has degree 8. This polynomial has degree 9. This polynomial, again, it's not always the first term, has degree 3, degree 5, degree 3. Just find that biggest exponent of the variable. All right, so, okay, good. That's what degree means. Thank you. So, polynomial of degree n has at most, and that's important, has at most n minus 1 turning points and n x-intercepts. Okay? So, if we just look at a polynomial, then we know a little bit about, maybe how many turning points it has. And so I think a lot of this is not as bad as it looks. Like this thing looks a little confusing. But if we just look at some examples, right? Let's look at some examples of some polynomials, shall we? If I look at some polynomial that says, let's look at x minus 2, x plus 1, x plus 3, why not? Okay, this is a cubic polynomial, okay, and it has this wavy shape. Remember, turning points are here and there. So this little property we said, okay, polynomial of degree n has at most n minus 1 turning points and n intercepts. So how does this translate to this picture? This says a third degree polynomial, a cubic polynomial, has at most, cubic is degree 3, has at most 2 turning points. And we can see that this one indeed has 2 turning points. It also says it has at most 3 x-intercepts. And again, for this problem, we can see all 3. Now this doesn't always happen. Right here we do have the maximum possible 3 x-intercepts and 2 turning points. Right, you can see, for example, if I change the polynomial to be not that, but this, it's still a third degree polynomial, and the theorem says, well, this has at most 3 x-intercepts. In this case, it only has 1 x-intercept. Okay? Or we could go back to one of our toolkit functions, right? This is a cubic polynomial too. This property says this has at most 3 x-intercepts and at most 2 turning points. But in this case, there are no turning points. There's no hills or valleys, and there's only 1 x-intercept. So again, the key word right here is at most. So we could kind of go back and talk about this stuff. How does the property work? This is degree 8. So this polynomial has at most 7 turning points and at most 8 intercepts. Right? This has at most 5 x-intercepts and 4 turning points. All right, and that's just a little property that we're going to be talking about a little bit, but not too much. We'll use it a little bit in the rest of the section, though. Kind of the end is going to be talking about turning points some more. So let's go into an example. Example 5. Determine the local behavior by finding the max possible number. Again, that's important. Max possible number. That's all that property tells us. The property doesn't tell us how many it's going to have, just the most it could have. Okay? The max possible number of X-intercepts and turning points. That's not how you spell that word. For this function. F of x equals 5x cubed minus 2x to the 5th plus x squared minus 1. And remember, do not be tricked. Okay? Sometimes these aren't all in order. So you don't just say, oh, this is degree 3. There's a 3 right here. Now you got to look for the biggest one. Similarly, remember on Friday when we were talking about leading terms? The leading term is only the first one if it's in general form. Here the leading term is this guy. The leading term is the one with the biggest exponent. Okay? So we need to use this property. But to use this property, we need to know what degree it is. So what degree is this polynomial in example 5? Somebody tell me. Anybody, please. 5. Thank you, Delaney. All right, so this is degree 5. So we use the property. A polynomial of degree 5 has at most 4 turning points and 5 x-intercepts. Okay? Yeah, much better than Lexi anyway. Lexi was sleeping for this problem. All right. At most 4 turning points and 5 x-intercepts. And that's all you do. Okay? All you do. Not good? Well, maybe she'll do better. All right, let's do another problem. Example 6. What if we go the other way, the backwards way, okay? What do we know about the degree of the following? And that's not being rude, it's just calling it like I see it, you know? Oh my word. He almost activated the microphone, he was so loud. My cat is getting whiny. I'm gonna give you a polynomial. Say it looks something like this. So, we're gonna use this little property and say, what do we know about the degree of this polynomial? We could also use information about end behavior, right? There's a lot of stuff we could talk about just looking at this graph and not knowing what we know about this section. So, how many turning points do we have? Turning points are the hills and the valleys. We have 3 turning points. So, that property says that we have at most degree 4, or at least degree 4. There are 3 turning points. Okay, the degree is at least 4. We also know some other things about this, right? We also know this is an even polynomial. And the even polynomial comes back from our leading term test for end behavior, right? Because the end behavior of this polynomial goes the same direction, it has to be even. Even is both up are both down at the outsides. All right. And because they both go up, we know the leading coefficient has to be positive. If you remember that table we talked about on Friday. Okay. So that's essentially what we have going on here. You hate end behavior. End behavior is not the worst thing in this class, but that doesn't mean you can't hate it, I suppose. There will be worse things coming up if that makes end behavior better. Let's do the last problem of this section, and then move on to the next. Should have a nice, light, easy, breezy day today. Okay, so example 7. Determine all local behavior. All right. It's supposed to be nice weather this week too, I think. So specifically by local behavior, I mean intercepts, degree, number of turning points, max number of turning points. 9:30 was actually fun? Hey, that's good to hear. I mean, there's the obvious implication that this is not fun, which is less good to hear. But I'll settle for 50%. So we got a function here. F of x equal to negative 4x times x plus 3 times x minus 4. Okay. So we just got to find all the stuff. We got to find the x-intercepts. We got to find the y-intercepts. We got to find the degree. We got to find how many turning points are there at most using that little property. Okay. So we're just going to do things one thing at a time. X-intercept is when y equals 0. So that's when is 0 equal to negative 4x times x plus 3 times x minus 4. Degree is going to be 3, yeah. This is our third class, Lexi, this is your time to shine, Lexi. Give me one or all of the x-intercepts. This is your time to show me that you are indeed one of the top students. Anyone else want to show me you're one of the top students? You can answer the question too, okay? But this is a specific call out. We got a polynomial equation we need to solve. Luckily, it's already factored for us. If this were not factored, it would be not so good. Those are 2 of them, Bella. Excellent. Top student, Bella. There's one more. I have it all wrong, Alexi? I don't think I do. What's the last 0? I'll give you a hint. Me asking for the last 0 is a hint. But yeah, we got 2 of them. Negative 3, positive 4, and 0. Excellent. All right, Bella and Lexi working together for success. That's how classes should be. So these are some x-intercepts. Y-intercept. Remember, the y-intercept is just when x is 0. This is even better, right? All we have to do is say, well, when is x equal to 0? And see what y becomes. We say, what is f of 0? That's when x is 0. We get negative 4 times 0, 0 plus 3 times 0 minus 4. Well, we got we got a whole bunch of stuff multiplied by each other. But notice this is a 0, right? This is 0 times 3 times negative 4. I don't care what numbers are here. That's a 0. So the y-intercept is also 0. And again, any time that you get either your x-intercept or your y-intercept to be 0, the other one has to be 0 as well, right? If x or y is 0, when it intercepts the axis, then the other one has to also be this situation. All right? Great. We found the intercepts. We still have to find the degree and the maximum number of turning points. Delaney already mentioned the degree. And the degree is 3. And that might not be It's easy to see. Is this pen running out of ink? I don't have a lot of pens. Hope not. I'll have to start like writing math in blood or something to show my dedication to my class. That's maybe not good. So the degree is 3 because look at the product, right? It's a factored thing multiplied by 3 things. Well, here's an x here, an x here, and an x here. When you multiply everything out, you're going to have an x cubed. Also, there's a neat, handy-dandy little secret that I will impart to you guys when we talk about 5.3, a little secret to finding out what the degree these ones are. So, that's another way of finding out the degree. You're going to learn it today, tomorrow at the latest. Okay? So, stay tuned for the secret. Anyway, lastly, we need to say, what is the maximum number of turning points? Also, by the way, you could also FOIL this and put it in general form. Yep, exactly. We use our property. Our property says a polynomial of degree n has at most n minus 1 turning points. So our polynomial has degree 3. So it has at most 3 minus 1, 2 turning points. Good. And that's the section. At most 2 turning points. We use capital letters to show how excited we are and confident in our answer. Good. Good, Lexi. Good, Delaney. Good, Bella. Good, Lane. Good. I was going to say Gabe, but I don't think he's here, so bad, Gabe. All right. Any other questions on this before we go on to the next section? All right. Let's get into 5.3 then. So again, we will finish 5.3 tomorrow. But 5.3 will not be on your exam. There's a long reason why 5.3 is not going to be on the exam. It's not that long, but I'm not going to talk about it right now. But 5.3 will be on exam 3, not 2. Not on exam 2. Okie dokie. But there's still elements of 5.3 that are going to be helpful for you when you do take the exam. So it's still worth, I don't know where I'm going with this. Let's talk about 5.3. So 5.3 is graphs of polynomial functions. And I know you hear the G word and you get nervous, you tense up. You start freaking out. Your sweat starts flying down your face, dripping off of your nose, off the chin. Okay? But it's not as bad as you might think. Okay? Because you're not going to be actually graphing that much. Well, you'll be graphing a little bit. Okay? But this section's not as bad as you think, and the graphing's not going to come until tomorrow, so we have that at least. It's a problem for future you. Okay? So, we're going to be sort of putting everything together that we've talked about in this chapter. Okay? We're going to talk about local behavior. We're going to talk about end behavior. We're going to look at intercepts, turning points, zeros, Y-intercepts. I just said the same thing like 4 times. Okay? We're going to put it all together, stir it up in a nice soup, and it's going to be the most delicious meal you've ever had. That's 5.3. It's a homemade delicious lunch. And then chapter 6 is when we have a nice dinner. Okay, like a 10-course dinner. All right. Future you's not excited? Well, don't worry about it. Present you can be excited. All right. Live in the present. Don't worry about the future. So we're going to start this. We're going to start this with something that's going to feel a little familiar. You're going to say, Jason, did we actually move on to 5.3? Or are we still in 5.2? I can't tell. Well, let's look at this. Example 1. Find the intercepts of the following. Part A. f of x equals x to the 6th minus 3x to the 4th plus 2x squared. And again, you say, Jason, we did this in example 5. This is not 5.3. This is the same stuff. Okay? I can't send you guys food in the mail. My whole class eats weird things like fried pickles. All right? You don't eat normal things like pizzas and hamburger and scrambled eggs. So the reason why this is different in 5.3 is now it's not given to you factored, okay? So you're going to have to remember how to factor. And I know you know how to factor because I know your Math 930 class was top-notch, phenomenal. And you learned how to factor in those, okay? So you say 6th-degree polynomial. Oh, I don't want to factor that. But don't worry, because we can take out a greatest common factor, right? What do all of these things have in common? There's an x to the 6th, a negative 3x to the 4th, a 2x squared. So we're going to factor out an x squared. They all have an x squared in them. And then what are we left over? We have an x to the 4th now, minus the 3x squared, then plus a 2. And you go, well, Jason, we certainly have not factored 4th degree polynomials before, but it's basically the same. Notice, this almost looks exactly like a bunch of stuff we factored before, right? But the numbers are twice as big in the exponents, right? If this were x squared minus 3x plus 2, we'd know what to do. But it's not. But it's still fine to factor. All right? The difference then, again, this x squared is sitting on top. The difference then, instead of being x and x, it's going to be x squared and x squared. Oh, Lane. And you just factor it the same way that we've done it before. All right, so the last sign, we look at the last sign and say, that means they have to have the same thing. The same signs going in both places. This negative means they're both going to be a negative. We need something that multiplies the 2 that adds to negative 3. Negative 2 and negative 1. And say, hypothetically, say you're not confident in your factoring. You could FOIL it out and check your work. And you say, oh, wow. I am so relieved that we finally finished factoring this. Finally finished factoring this fun problem. Okay, but we're not done yet. We could factor it again, right? But you don't need to. You could factor it again. It's your choice. All right. We need to find the intercepts. And that's what we're doing. Factoring helps us find the X-intercepts. So let's find those X-intercepts. X-intercepts are when x squared equals 0, when x squared minus 2 equals 0, and when x squared minus 1 equals 0. We need to solve all of these equations. 3 quadratic equations for you to solve. So this first one, right, we just take the square root of both sides. You get x is equal to plus or minus the square root of 0. Just x is 0. Next one, we add a 2. We get x squared equals 2. Square root both sides, we get x is plus or minus the square root of 2. Last one, add 1. Take the square root, x equals plus or minus the square root of 1, which is just 1. Do not forget your plus and minuses. These plus or minuses are very important. Do not forget them. Do not leave them alone. Do not leave them in the snow and the rain and it's cold outside. Let them inside. Give them a nice hot bowl of 5.3 soup. Don't forget your plus or minuses when you square root both sides. Okie dokie? So, those are the X-intercepts. We factored first. We took out a greatest common factor. Then we factored the inside, and we could have factored some more if we wanted to. All right. So you left your plus and minuses in Wyoming? What state are you in now? Are you in like Alaska? That's where I want to go. Alaska sounds like a neat place. Not a lot of people in Alaska. All right, so we need the y-intercept as well. Okay, how do you see this on the graph? I will actually show you right after we do the y-intercepts. Good question. All right, so the y-intercepts are when x equals 0. And remember what our function looked like, right? F of x was x to the 6th minus 3x to the 4th plus 2x squared. So the y-intercept is easy. Easy street. We already did the hard stuff. We already did the hard stuff. Kind of boring? Yeah, I'm kind of boring too. I'm kind of a boring guy. Let's see. So when x is 0, what do we get? We get 0 to the 6th minus 3 times 0 to the 4th plus 2 times 0 squared. And that's a whole lot of zeros, my friends. 0. Again, what did I say? I said anytime you have one intercept being 0, the other intercept's going to be 0 as well. So y-intercept is 0. We found the x-intercepts, we found the y-intercepts, and we're good to go. Now, fun fact, Wyoming is the least populated state, but Alaska is the least densely populated state. There's more people in Alaska, but it's a way bigger area. All right, so let's look at this function, okay? We had y equals x to the 6th minus 3x to the 4th plus 2x squared. Ooh, this is a funny looking graph. What do we say? We said the x-intercepts were 0. This is where it crosses the x-axis. Yep, it crosses the x-axis at 0. We said positive and negative 1 crosses the axis at positive and negative 1. We also said positive and negative square root of 2. That's this one, 1.414 approximately. All right. We also talked about the y-intercept. Where does it cross the y-axis? Right here, 0, 0. Yeah, Alaska is gorgeous. What are some other things we talked about? How many turning points does this have? This is not part of the problem anymore. How many turning points? Hills and valleys. 1, 2, 3. Almost missed that one. 4, 5. So since we have 5 turning points, that this polynomial must be at least degree 6. And again, the polynomial is degree 6, x to the 6th. Okay? That property also said we have at most 5 zeros. And again, we have 5 zeros. Okay? Or at most 6 zeros. The property said we have at most 6 zeros, and we have 5. That's okay. At most 6. 5 follows that. We're also going to talk about something new, and I'm going to get a little bit ahead of myself. A little ahead of myself. Notice there's a difference. Notice it crosses the x-axis here, crosses here, crosses here, crosses here. But notice it just lightly kisses it at 0, lightly touches it. There's going to be something different. Is there something unique about these 4 zeros and this one? We'll talk about what that unique thing is that separates the crossing with the... Goodness. I don't know how to say that. We'll talk about that after part B. All right, let's do another one of these. All right, another one of these. Part B. Okay. G of x equals x minus 2 squared times 2x plus 3. Oh, this one's already factored for us. That is great. All the hard stuff already done, right? X-intercept is when y is 0. So that's the solution to this equation when y is 0. When is 0 equal to x minus 2 squared times 2x plus 3. Okay, and you know how to solve that. That's when x minus 2 is equal to 0. And when 2x plus 3 equals 0. You just solve these equations. X equals 2. solve this equation, you get negative 3/2. I trust all of you to be able to solve this linear equation, so I'm not going to do it right now. There are 2 zeros right here. 2 X-intercepts. All right. And again, we can find the Y-intercept a similar way, right? Y-intercepts is when x equals 0. So we just plug in 0. G of 0 equals, this becomes 0 minus 2 squared times 2 times 0 plus 3. That's negative 2 squared times 3. Positive 4 times 3. The Y-intercept is 12. And that's how you do it. If it's not factored, you're going to need to factor it. If it is factored like part B, it's much easier. So let's look at what the graph looks like for this one. Okay. Here now, we have x minus 2 squared. Whoa, not that. X minus 2 squared times 2x plus 3. Oh. Oh man, this one's big. No, it's not that big. I was just super zoomed in. All right. So notice again, this is a cubic polynomial. The degree is 3, right? Because there's an x squared here and there's an x here. The degree is 3. It looks like a cubic polynomial. So that means at most 2 turning points, at most 3 zeros. We do have 2 turning points here and here, but we do not have 2 zeros. We do not have 3 zeros. We only have 2 zeros. That's okay. And again, notice the difference right here at the 0. It crosses. At the negative 3/2, it crosses. But at the 2, it just bounces off. That's a good way of saying it. Bounces off. Okay? So we can look. Is this a coincidence? Let's check. What if we get rid of this 2 here? Get rid of that 2. Let's not get rid of it. Let's turn it into a 1. Right? Now it doesn't bounce off anymore. Right? Notice now it crosses both of them. Let's go the other way. If we make this have an exponent of 2, oh, now it bounces off both of them. That's something we're going to call multiplicity. Okay? It was not a coincidence. If you thought it was a coincidence, you have been surprised. All right? Multiplicity, how many times we have a 0. Okay? So that's what the definition and property that we're going to go into right now. All right? So, here we go. What do we have right here? We have property. Like boardwalk. This property is like boardwalk. Everyone loves it. Now this property is like income tax and monopoly. I always thought income tax was the dumbest square on the entire monopoly board. Just my own opinion. Maybe that'll be a attendance question today. All right, property. Whew. If a polynomial has a factor x minus h to the p, we got 3 things we can say. Whoa! All right, it can't be boardwalk because there's 3 parts. It could be like the green ones. I didn't actually play standard Monopoly a lot. I played Star Wars Monopoly, and the green ones were Endor. Go to jail. Well, that's not a square. Oh yeah, it is. It's one of the corner squares, huh? Go to jail is funny. It's funny when going to jail and having to pay for your houses. Those are funny when other people land on them. Income tax is just never funny. I don't know. Maybe I don't know. I sound like a socialist or something. Or not a socialist. Something else political. I'm not going to make a political joke. Anyway, here we go. We have 3 things. If a polynomial has a factor of x minus h to the p, what happens? three things. Oh, oops. This is like boardwalk. There's only two things here. The third one will be, then you can smile. That'll be the third thing, okay? I'm adding onto this property a little addendum. First part of the property is x equals h is a 0 of multiplicity p. So multiplicity is a definition, and it's has to do with this thing up here. Okay, the second one, you're just gonna have to wait for the sequel because we want to talk about it first. Let's talk about this. Okay, let's talk about this graph. Let's look at, oh my word. Let's just look at something again, x minus 1 times x plus 2. Now, these both, right, the zeros are x equals 1 and x equals negative 2. They both have multiplicity 1. And look at how they look, multiplicity 1. What if we make this 0 have multiplicity 2? Multiplicity means we add an exponent, multiplicity 2. Oh, sorry, not that 0, this 0. Now that it's multiplicity 2, it does not cross anymore. It bounces off. What about multiplicity 3? Multiplicity 3, it crosses, but notice it crosses kind of like a cubic function, kind of like our toolkit function, right? Remember the toolkit function x cubed. This is that same situation, because notice x cubed really is just this situation, right? We could write x cubed as x minus 0 cubed. X cubed, our toolkit function, this is exciting, has a 0 of 0 with multiplicity 3. And notice when we add an x cubed, it looks like our toolkit function right there. What about multiplicity 4? What does multiplicity 4 look like? Is there more? Yeah, multiplicity 4 kind of looks like multiplicity 2. All right, it kind of looks like a parabola just bouncing off, just a little flatter. The interesting thing about the gasps here is you can hear them so much louder than you can in class. Like if I gasp in class, you just hear, but if I gasp while I'm teaching online, you hear the full. So again, what about multiplicity 5? Well, again, it kind of just looks like a flatter cubic function. Multiplicity 6, just like a flatter quadratic. Okay, this is boring. We get the idea, Jason. 7, kind of like a cubic function, just flatter. 8, kind of like a parabola, just flatter. 9, yep. It's flatter and flatter the more multiplicitying you get. So let's add that to our property. That is the sequel. That is the part 2 of the property. Okay. If P is odd, yeah, we'll add on to the property again. If P is 1, the function crosses like a line. Oh, I don't really have enough room for this. If P is odd, 3 or more, and odd, it crosses like x cubed. If it's even, it bounces off. All right, I got a little wordy over here. Okay. I got a little wordy. But I'm just trying to explain. If it's 1, just crosses normally. If it's odd, it goes kind of like that. If it's even, it goes boing like that. Okay. Those are the official sound effects of polynomials. So here's what we're going to do. 2 more examples, both with A's and B's. Then we're going to be done for the day. We'll be done early. Okay? So let's use this stuff. Use it with example 3. Find the... You're going to have a funny reaction to this. Find the maximum number of turning points for the following. And again, you might say, Jason, we already did this. This is 5.2. And yes, these sections are like this. They're so interconnected. It's like a section part A, section part B, okay? They're very similar, okay? But again, we're just going to state these problems in a slightly different way. And we can talk about degree, zeros, multiplicity. We're going to talk about all of that together. Okay, so part A is going to be f of x equals negative x cubed plus 4x to the 5th minus 3x squared plus 1. Also, part B is going to be f of x equals negative x minus 1 squared times 1 plus 2x squared. Okay, so think about these. Find the degree. Find the maximum number of turning points with that property. Think about how that interacts with multiplicity and what the zeros are. Also, attendance question today is to pick a type of weather. Rain, sunshine, clouds, hurricane, monsoon. All right, some type of weather. That'll be the extra credit question for today. So go ahead and do that. Think about these 2 problems, and I promised all of you a wig for today. All right, I will go get the wig while you are studiously answering example 3. All right. So this wig is pretty cool, right? The hair goes all over the place. You wonder, what would Melon look like if he had blonde hair? What would Jason look like if he had blonde hair? Woo! And this is the answer. Okay? Yeah, I see it, Lane. I see it. All right. Oh! All right, we're not finishing with that, though. I'm embarrassed that I called myself by my gamer tag. Not paying attention. Yeah, that's a wig I got to do make fun of the character Ezreal from League of Legends. Okay, so hopefully you did these problems. All right, hopefully you did them. Max number of turning points. Degree, right? This is the leading term. The degree is 5. So 4 maximum turning points. Max of 4 turning points. We'll abbreviate that TP. Really fits with the state of the world right now. Put it back on. You know what? I will put it back on. We don't have that much of class left anyway. I don't know how people have hair. How do you people live with hair? It just gets everywhere. Well, look at this. It's like me, I have glasses. Glasses are like PPE right now. Okay? So, there we go. It's beautiful. So similarly, right? Careful with this one. Careful with part B. Someone make a guess, and you might be wrong. What's the degree of the polynomial in part B? Someone tell me. It's okay if you're wrong. I do have at least one long hair wig, at least two long hair wigs. It's not 6. It's not 3. Because notice what we have here. This one, it's kind of hiding. Right? This has a 0 of 1 and multiplicity 2. Yeah, it's 4. Uh-huh. And this has 2 zeros. Degree is 4, so at most 3 turning points. So essentially, what you can do, I really wish I had room to write it right here. Okay? What you can do here is just count up all the zeros and the multiplicity. So 1 0 here, multiplicity of 2. So we already are at least 2 for our degree. And then over here, how many solutions are there to this? 2. 2 plus 2 is going to be our 4. Talk more about that later. If I were Asian, I'd look like a little anime character. Yeah. This is my anime boy wig. Do the last example. Hold up. This is example 3. We never did example 2. Example 2 is going to be our last example. Don't worry about the order. All right. Example 2. Identify the zeros. And their possible multiplicities. Because we don't really know. We said if the multiplicity is 1, it just crosses. If the multiplicity is even, it bounces. And if the multiplicity is odd and at least 3, then it kind of zoops. The only thing I know about Dragon Ball Z is that like half of the episode is just these guys, and they just go, and that's like half the episode. It goes on for like 10 minutes or something. I'm not a big anime fan, but it's something like that. I need like a fan blowing my hair up or something. And that's what happens. That's anime to me. Or at least that kind of anime. So, last problem, part A. Find the zeros and identify possible multiplicities. Okay. So let's say polynomial looks something like this. Say we're looking at a polynomial that looks like this. Thanks, Lane. So, let's say this is 1, 2, 3, -1, -2, -3. So we have to find the zeros and find their multiplicities. And again, we don't really know multiplicities, but we can kind of guess. So the zeros are just the X-intercepts. Where does this cross the X-axis? Zeros are going to be right here, right here, and right here. These are the only places the graph crosses the X-axis. So -3, excuse me, -1, and 3. All right. And now we just have to talk about multiplicity. So remember, even multiplicity is when it bounces. All right. So this is going to be even multiplicity. We don't know if it's multiplicity 2, 4, 6, or whatever, but we know it's even multiplicity. What about this one? Well, certainly not even, but it's not the same situation as this either. This crosses kind of like a line, and this crosses like a cubic function. Okay? So the multiplicity of this one is just going to be 1, and the multiplicity of this one is going to be odd. But we don't know what odd number. Some odd number, at least 3. Okay, look at this. That's how we do these. You don't have to write respectively, but it's kind of good habit, right? So -3, -1, 3 have multiplicity even, 1, and odd respectively. Respectively, when you have like 2 lists, means that the first thing goes with the first thing, the second thing goes with the second thing, etc. So 1, it goes back to the property. Essentially, if the multiplicity is 1, it crosses kind of like a line. But if it's odd and at least 3, then it crosses like x cubed. So over here, it does like, right? If we zoom in on the function, it kind of looks like it could be like a steep line. Whereas this one, if we zoom in on the function, it kind of looks like a cubic. Okay, so that's kind of what's going on there. Good question. Any other questions on this before part B? Part B is a real wavy boy. So, part B, let's say we have something like this. Kind of goes through it. Then it bounces. Then it gets really flat, like that. Okay. And in this problem, we have 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4. Kind of hard to see. So again, the zeros are just where it crosses. It crosses at -6, crosses at -1, crosses at -4. Obviously, on your quiz, you will not have hand drawings. You will have actual graphs that you will be able to read a little bit more clearly. The zeros are when x equals -6, -1, and 4. And the multiplicity for -6, it's going to be something odd that's at least 3, because it kind of looks like a cubic function. For -1, it bounces off. It has to be even, like a parabola. And this one bounces off, and it's really flat. So we're just going to say it's also even, but we know that since it's so flat, it's going to have a higher multiplicity. The higher the multiplicity, the flatter it gets. Okay? All right. On probably high multiplicity. You don't have to include that. This is apparently one word because my space bar is broken. My space bar on my hand. All right. That's what we got for these ones. And again, if I gave you another one that maybe looked like this, right, these would all have multiplicity 1. Because if you kind of zoom in on the function, kind of like a line, zoom in kind of like a line, zoom in on that 0 kind of like a line. So all of these would have multiplicity 1. All right. All right. This is I'm never wearing that again. So that's the section, half of the section. We're going to get into the graphing part tomorrow. Tomorrow we're just only finishing this section, and then if we have some time we'll review for the quiz, and then you'll have a quiz tomorrow on 5.1 and 5.2. Okay? Any questions for me before we go? Because that's class. That's class today. We already did the attendance question. Bella, were you not listening? Oh no. The attendance question was weather. Give me a type of weather. Ha ha, oops. Yeah, I should do one of my patented loud gasps. Anything else before I get off and write your exam? I have a great afternoon ahead of me. Writing your exam and making the solutions for it. Whoa. All right. Looks like there are no questions, so have a fantastic day. We are just about halfway done the class. Your other classes may be more than halfway done, depending on how they go. But we are going to be going a little late in our semester. Beautiful day outside. Have a good day. I will see you tomorrow. Tomorrow will be another fun day full of graphing. Please be in a good mood while I write. Well, it depends on what comments you sent me for your attendance question. If you got me interesting weather, I'll be happy. If you sent me something lame, maybe I'll make a hard exam. All right, bye.